The broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, everybody, and this is Dr. Mansour, and today is May the 17th, and this is Sunday, and this is our meeting for the seismic review. So, per our schedule or per our brochure, I believe we are having today from 1 to 5 for the seismic review based on the new code, which I have all my books based on that, the IBC International Building Code, CBC, and ASC 7-16, which is the critical one here. Let me get something very quick here. This is a brochure for the fall or summer and fall, and for the seismic. Just coming, here we go. After this, immediately the seismic. So today is the 17th of May. So before I covered from chapter 1 to chapter 5, and we talked about a lot of problems, or solve a lot of problems, either from the textbook or from the 6 to 6. The 6 to 6, this is a book that I compiled all the problems that I generated over all these years, and I put them in one book. I call it 6 to 6. So from the other two books, another book is called the 300, and another book is called Seismic Practice Exams and Solutions. And I put them in one book. It's called the 6 to 6, and this is a CPT format. And normally we send you a USB, and the USB, it has a program where you can generate unlimited number of exams. Each exam is 55 questions, as indicated on the cover. Random. Probably I didn't put the word unlimited here because probably my lawyer was objecting to the word unlimited. But in some situations, you will find that many, he said that many. So we call it random CPT exams, 55 questions each, will be generated, graded, and scored. And I hope the program is working fine with all of you. This is a color cover. This is not color cover. This is the difference, but essentially the same. So chapter 6 is very important chapter because, as you know, this is a seismic design for building structures. So the code, the current code, as all of you know, is divided into building structures, non-building structures, non-structure components, and they cover shearing walls and diaphragms together. So, so today is 5/17/20. I hope that everybody is healthy, and I don't know when they are going to open again the barometric sites or the testing sites to resume giving the exams again. I didn't check them recently, so I wish you the best, whatever the decision will be. And whenever date you are going to take the exam, I am here to help. So the seismic code, the ASCE 7-16, which is the main one, they have several chapters related to seismic design, but you can say that they are or they can be compiled or can be grouped into 4 groups: building structures, building structures, building structures. And after that, this is chapter 12, 11, 12, in fact, of the ASCE 7. Chapter 13 is talking about non-structural components, non-structural components. These are the architectural and mechanical and electrical. So this is the second category. This is the first category. And the third category is non-building structures, non-building, which is chapter 15. And we do have a separate document is talking about shear walls, and diaphragms. Shear walls and diaphragms also they mentioned in chapter 12 of the ASCE 7, but the reference is to the special design of provisions for wind and seismic of 2015. So we're still using 2015 of the special design of provisions for wind and seismic, which is this document here. Even if you have 2018, they are still using the 2015 of the special design of provisions for wind and seismic. So in my textbook, I covered from chapter 1 to chapter 5. Chapter 6 is the seismic design requirements for building structures. And the best way to handle this is to go over problems, because those who are taking the class with me, you have unlimited access to the on-demand, and I hope that on-demand is working with you fine. If you have any problem, please email me and I will talk to my staff. They are working remotely, but they can still help by solving any technical difficulty or any technical issue. But as far as I know, the system is working fine. The course I taught it in the first quarter. It is recorded. It was recorded and it was loaded on the server, and it is viewed for 24/7. So it is available for you 24/7. And I hope that, as I said, that everything is working fine. So the title for this chapter, which is chapter 6, seismic code requirements for building structures, based on the ASCE 7 chapter 12. You can say also chapter 11. Chapter 11 of the ASCE 7, chapter 11 also, it does have the basic equations. Chapter 16 also has the same basic equations of the IBC or CBC. And normally I go with the IBC. IBC is much simpler and cheaper than the CBC. So, but it's your choice. If you have California Building Code, Volume 2, you can still use it in conjunction with the ASCE 7-16. So the building structures, as all of you know, those are the structures that consist of lateral force resisting systems. So if we take this group here, which is the first category, seismic design for or seismic design requirements for building structures. Building structures. This is chapter 6 of my textbook, which is based on chapter 11 and chapter 12 of the ASE 7 and chapter 16 of the IBC or CBC. So the code, our objective from studying the seismic requirements for building structures is to get what is the seismic base shear first. So our objective is to get the V. So if this is the base and whatever the number of stories, so the objective of the code is to get what is known as V. And V is a seismic base shear. So the base shear is the first component, base shear. Let me write it down. So the seismic base shear. So this is the main target or the first objective is to get the base shear. And the base shear, the V, the current code, they can get it or it can be determined using 3 methods. The dynamic analysis, which is basically force is equal mass time acceleration. So if you are giving the acceleration directly in the problem, or they have a response spectrum to get the acceleration, you can use this, and I can go over this right now. Okay, the first thing that I will select a problem that has dynamic analysis. And the second one is called ELF, equivalent lateral force procedure. They came and they said that this is really costly as far as the dynamic analysis and time, it takes time, but it is the best. Okay, and this is why any structure, any building structure can be analyzed using the dynamic analysis, but there are certain building structure must, okay, analyzed using dynamic analysis as given in a flow chart. I can go over the flow chart to show you how can we determine if this structure is eligible for the dynamic or for the ELF. ELF is the abbreviation for equivalent lateral force procedure. Equivalent lateral force procedure. And the objective from using the ELF to save time and money. Okay, because not every single structure has to be analyzed. I have Mr. Mansour has 2-story building or 3-story or 4-story building. Okay, a very simple building and is supported with a good soil and it's a very good site. And there is no too many seismic activities, or it does not meet the requirement for the dynamic. Let me put it that way. So they said there is no need to analyze this structure using the dynamic, because dynamic you have to make a model like the wind tunnel test when they test a new plane or a new space shuttle or a new any flying engine. They do wind tunnel test. They put this new plane into the wind tunnel test and they test it and they see how the plane will behave. For the dynamic, they do the same thing. We have a mechanical shaker, and I probably saw it on the YouTube, and they put a model of the structure. If the structure is 15-story building or something, they make a small model of it, and they put it and they shake this model, small scale of the actual building, and they shake it with the mechanical shaker at different values of acceleration, and they generate the response spectrum. We cannot do this for every single structure because, as I told you, it is a time and money. So they came up with the ELF, where they came up with a generic response spectrum. Because here, from this mechanical shaker process is to get this. This is the time, and this is the acceleration. If we can generate the response spectrum for any given structure, became piece of cake. Because for any period, I can go up and hit this and get the acceleration. Acceleration is here. I have the mass, piece of cake. Let me locate a very quick problem from my 626 book, just to illustrate to you what is meant by that. Hopefully I can, too many problems, and sometimes I try to locate I say I saw this problem here before, and I remember where it is located, but sometimes the memory, okay, it doesn't give me a full speed, but we will locate some and we will solve it together. Okay, like this. Here it is, problem 392 of the 626 book. They gave us this. I will get closer to this. What is this? This is the response, design response spectrum, or if I have more than one, design response spectrum, Brora 4, which is a relationship between the period of the structure, or the period of vibration, versus the acceleration, spectral acceleration. The moment you see this given in the problem, immediately they are telling you get the dynamic analysis. Dynamic analysis, because we normally ask ourselves, how I know that if the problem he wants me to solve it using the dynamic, which is the first one, or the ELF, or the third one is a simplified. They call it alternate design method. This is number 2. This is number 1. Number 3 is called the alternate method, alternate design, or we call it simplified. And this is the third one. And on the exam, you have to, when you read the problem, the actual exam, the moment you read the problem, you have to make a determination which method is going to be selected to solve the problem. Because it will tell you the design-based shear is most nearly, and that's it. Okay? So the moment you see something similar to this, the response spectrum, the relationship between the period and the acceleration, immediately I will think about the dynamic analysis. And I have a lot of problems related to or having response spectrums, and here it is. For example, here it is another example, probably a little bit bigger and much cleaner. Problem number 318. Number 318. And the 319. So 318 is asking what is the period T, which I will talk about it after that. And problem 319 is talking about this frame is given here, and is asking the design base shear is most nearly. So he would like to get V, the design base shear. He didn't tell me the design base shear based on the dynamic analysis, or pair the dynamic analysis, or according to the dynamic analysis, or according to the ELF, and so on. No, he told me that I need the base shear. But this is given here. Since this is given, which is the period, the natural period versus the acceleration. The moment I see that, immediately, this is a dynamic analysis approach. Dynamic analysis approach. So the response spectrum is the one will guide me or tell me. But in another problem, like this problem here, let me see here, the story shear, the period. Okay, this is a period, and here it is. Another problem. Problem number 330. He gave us a structure. This is a building structure. He gave us the weight W. And he told you the design base shear has been calculated for you. And it was given to be this amount. And he's asking what is the story shear? Story shear. And we're going to talk about the story shear. But I need to get the problem that it's asking for. Here he gave you the story, the base shear, the design base shear V was given to you. But he can ask you to calculate it. The same problem is repeated again, and they're asking you what is. So there is nothing really associated with it as far as the response spectrum. So I need, in this case, I need to get the okay. This is something that I needed to be aware of. So let me go to my note here, and after that we'll solve problems. Because so the dynamic analysis, I should get something, okay, response spectrum like this. For the ELF and the alternate or the simplified, what they did, the code, the E7, or in fact it came from this famous document by the I will show it to you in just a minute. So what they did, they said that if we can come up with a generic, and they did that, generic response spectrum, FEMA, they hired a lot of scientists and engineers and seismologists and structural engineers, and they professors, and they did a lot of research, and they came up with something. They call it the design response spectrum. And this design response spectrum, a generic one, and it's given like this. Which is given in the ASE 7 chapter 11, figure 11.4-1. So instead of devolving one for each structure based on the dynamic analysis or the mechanical shaker behavior, they came up with a generic one. And they call it the design response spectrum, where this is a period T and this is the acceleration. And this was developed over years. And so here they call it, this is T sub O. This buried here, they call it T sub O. And this is T sub S. And this is called T sub L for the long. So we have T sub L and T sub S and T sub O defined for us by the code. T sub L is given, by the way, in a graph. T sub L for the long buried T sub L in California between 8 to 12 seconds. So there is a map for showing that. I'll show it to you. But T sub S and T sub O will take it 20% of T sub S. And this response spectrum is divided into four regions, 1, 2, 3, 4. And what I did, I took this response spectrum in my book and put it and modified. And for those who took the class or those who are attending or viewing the webinar, they are aware of this, which is this one here. But I modified it a little bit and tried to add. This is for the ELF. This is ELF, as indicated in the title here, ELF. The equivalent lateral force procedure, ELF, which is a majority of the structures will be analyzed using this. So these are the four zones or four regions, I call it. So if we are able to locate which region I am in, I will use the appropriate equation or equations. Okay, so this is 1 and this is 2, and let's color the other region here. Leave this here. So this is region 4 here. This is 3, I will leave it, and this is 4. So if we are able to determine the structure period T, and I will decide if I am here or here or here or here. So I'm using the appropriate equation or equations with the limitations given in the code. But the basic equation, which is this one here, that the V is equal C sub S times W. C sub S, it does have a name, it's called seismic response coefficient. Seismic response coefficient. W is the seismic dead load. Dead load, which is the weight of the structure with all bearment attachment to it, plus some other components. I put it in a table form, but it is listed in the code as item 1 through 5. So this is the whole story. So this is for the ELF. The simplified, which is the third one, the simplified or the alternate design method, as they call it, it does have 12 requirements. 12 requirements must be met in order to apply the simplified one. You don't have enough time during the exam to go over these 12 requirements. And this is what I'm expecting, and this is what I heard, that if there is a problem and they ask you to solve it using the simplified, they will tell you solving your problem using the simplified or the alternate design method, assuming that all the 12 requirements have been met, because you don't have enough time to do verification or to check these 12 requirements. Okay, and what they did, they took this, by the way, this is called SDS, the acceleration for the short, and at 1 second here somewhere we have what is known as SD1. SD1, because those are the two parameters for design. It's called design acceleration. So design acceleration SDS and SD1. Those are the design acceleration. And there is a process to get them. I provided you with a table to get them. And we'll talk about this in the class, and I'll be glad to go over them again to explain this. So the key here is to read the problem carefully and look for all the keywords, because I used to write a lot of questions the last 30 years, some of them for the board, maybe way back. Keywords. Very, very important to look for the keywords. Each exam problem has some kind of keyword or keywords. Try to focus and get and pay attention to the keywords, because they are looking for something specifically, and this is what you should focus and you should solve the problem based on that. Okay, so the problem, that the one I was talking about, I'm gonna start with this problem here, problem 318 first, because we need the period. So if you don't have the book, you are very welcome to read it, and I will be glad to attach, even if you don't have my book, attach the notes, my handwritten notes. Normally I do that. I hope that I am up to date as far as sending you the notes. If you did not receive my notes for the last lecture, please remind me. And as I told you that I don't have a staff here in the office, I do all the work by myself, so I'm still doing all my best in this period or these tough days. So go ahead and read the problem, and let me. Okay, so the frame shown consists of two columns and a rigid plate. This plate is rigid. The two columns are made of steel. The W section, W, as you remember from steel design, the W shapes. The first number is representing the depth, and the second number is representing the weight, how many pounds per linear foot. The first number is not exact, but the second number is exact. So the first number is the average depth, the group depths together. So this is a W shape. So this is the depth from here to here. So they group them together, but the actual depth, you have to go to the steel manual, and to get it is 15.9 or 15.92 or whatever it is. But the second number is the weight. How many pounds per linear foot? But this is exact, 36 pounds per linear foot. And he gave you the I sub x and S sub x. Why he didn't give you I sub y and S sub y, by the way? Because as you know, each section, it does have two axes. This is xx, and the vertical one is a yy. We know that from the steel manual or from the structure analysis classes you took, yy. But he gave me the xx, because xx is a strong axis. We have something is called the strong axis bending and weak axis bending. We put the shapes like W shape, like this W shape, or the I-beam, as you like to call it. We put it in the position to get the maximum benefit of it, called strong axis bending, where the moment of inertia is the highest along this direction. Okay, so this is what, because you will never see a beam like this, okay, because this is will be waste of resources and waste of money when you have a W shape, that I put it that way. So try to draw it. Okay, this is not the right direction or the right position. So the right direction or the right position is to put it along the strong to get the maximum benefit, because so this is the XX and this is the YY, as all of you know. Because if you look to the equations, either stress sigma is equal MC over I, this famous equation. So the stress is inversely proportional to I. The larger the I, the smaller the stress. And this is why I'm using IX, because this one here, IXX, is much, much larger than IYY. Okay, so if you look to the steel manual, let me grab one of them. Just to remind you, this is the steel manual. This is the 15th edition, no, 14th, the grade one. So if you go to any section, any W shape, grab any W shape here, just to illustrate. This is still C. HB, here it is W shapes. Okay, for any shape, this is how it looks like. And if you look to the XX and YY, for any given section, it doesn't matter. You will find, for example, this IXX is 1490 inch to the fourth, but the IY is just small, 186, and so on. This is 954. This is just 119. So this is called the weak axis bending. Weak axis bending. This is a strong. So they gave you, here it is, and this is the designation for the XX and YY, as all of us know. Just a reminder with what. And this is why they gave you, and the second equation that we need is a deflection. The deflection, because we look for stresses and for deflection. Because I don't like my beam or my structure to sag under the given load. So the deflection must be within the acceptable range. So deflection also, for example, for uniform load, as you remember, there's one famous equation, 5WL to the fourth divided by 384 EI. This is another equation. And you can see E here is the moment of elasticity, and I is the moment of inertia. Also, the larger the moment, the smaller the deflection. So the stress is inversely proportional to 1 over I, and the deflection is also inversely proportional to 1 over I. So the larger the I, the smaller the stress, and this is what I would like to achieve. And the larger the moment of inertia, the smaller the deflection, and this is what I need to achieve. I need to get my stresses and deflections are the minimum by using the proper orientation of the section. And this is why in the problem here, he didn't bother to give you the I Why? So this is why I just explained to you why. S, by the way, is called elastic section modulus. S is called elastic section modulus. And this is basically, it is I over C inch cubed, because I is to the fourth and C is a distance from the neutral. This is C here. From here to here is C. C top and C bottom in this case are equal because it's a symmetrical section. Just something on the side. So each column is 12 feet. The weight of the top girder or top rigid blade is 168 kips. And he's asking, so the weight here, W, is 168 kips. As you can see here, I draw the deflected shape. This dotted line here is the deflected shape because of this lateral force. This is the seismic lateral force. Seismic lateral force. It has been hit by this seismic lateral force. Originally, the force is here, by the way, which is a base shear. And this is one story, as you can see. So this force at this level, so it is V and F are equal in this case. As you can see here, this angle was indicated to be 90 degrees. And he used the word rigid. The moment you see the word rigid is indicating fixed end condition. Because this, it could be either fixed bottom and fixed top, these columns, or fixed bottom, hinge at the top, or it could be fixed at the bottom, free at the top. This is FF, and this is FH, and this is just only F. And you can say free, dash free. So for each end condition, depends if the column is fixed at both ends, or fixed from one end and a hinge on the other end, or fixed here and free here. Each one of these, it does have what is known as K. K is a stiffness. K is a stiffness, a stiffness, a stiffness. So we use stiffness for columns. We use rigidity for shear walls. You have to differentiate between them. So any member has a resistance. If it is a column, a part of a frame, or a shear wall, so they decided to use R for shear walls, which is rigidity, which is 1 over delta. Columns, they have something called stiffness K. K, stiffness. Stiffness. What is a stiffness? Stiffness is the force required to produce a unit displacement. As you remember from class, stiffness, it is the force required to produce a unit displacement. And we remember from school the spring stiffness. When you have a coil spring like this, do you remember the coil spring that we did it in physics 4A or 4B? You have a spring like this, coil spring, and we apply a force, B or F, whatever you call it, P. If I compress this spring by a force, it will deform. If I increase the force, the deformation will increase. If we plot the B delta curve, as we call it, P delta curve, force P versus displacement or deflection. Some books they call it X, or some textbook they call it X. We have a linear portion at the beginning, and after that we'll go into the non-linear, but we are interested in the linear portion. So the slope of this line is called K. K is equal P over delta. Slope of the line, spring stiffness or stiffness. But for columns like these in a frame system, in chapter 5 of my book and all other books, they have it, came from the same source. I give you a table, and this table shows the different stiffnesses for different end conditions. And this is the table here in my book in chapter 5, table 5-3 of page 154, if you have my textbook. Okay, this is the 5th edition. And you will find this table here is telling you what? The title of this table, deflection and the stiffness for columns and the breast frames. So those are the 3 cases I was talking about. That the column might be fixed at the bottom and at the top, which is called fixed, or it may be fixed top and hinge bottom, or reverse, or vice versa, or fixed free. So any of these conditions, it has an associated stiffness K. This is a K, and this is a K, and this is a K. 12 EI over H cubed, or L cubed. H is the height or the length. So you should know where these things, because we need them. Why we need them? Because here he asks you to find the period T. So the period T, it can be determined using this basic equation, which is 2 pi square root of W divided by K. Or make it M, the mass over K, which is given also on the same chapter, or any, let me just make sure, make it M at least, and after that I will talk about the difference between M and W. So M over K. This is for a single degree of freedom system. M over K. We know W is equal mg. So the mass is equal W divided by G. So we can substitute here for the T is equal as 2 pi square root of the weight divided by G times K. This is a second form. So I start with M, and after that, this is from the structure dynamic, or from the basic formula. That it's mentioned also in the code in chapter 15. So it is, so the period T, what's the period? Period is the time required for a complete oscillation of vibration. This period T, structural period, structural period, we can determine from the Rayleigh formula, which is for a single degree of freedom, T is equal to 2 pi square root of M over K, or 2 pi square root of W divided by G times K. G is the gravity acceleration, and K is the stiffness. And in fact, this is given, by the way, if you look to the code, you will find that equation in chapter 15, and also I gave it in my books. It does have a general form. The period, it does have a general form, which is T is equal to pi square root of, instead of this simplified form, is the sum of the Wi delta I square divided by G of the sum of the Fi delta I. This is another equation. This is equation, by the way, given in the code 15.4-6, chapter 15 of the ASC 7. This is the general one. Wi, which is the weight, delta I square divided by G times Fi delta I, and I will show you a problem that we are solving. This is the general equation. For a single degree of freedom system, this, and I proved this to you in chapter 6, how did we come from here to here? This for a single degree of freedom system, single degree of freedom. Also, if you remember, also for building structures, that the period T, there is other 3 approaches, but they call it T sub A, approximate. Because here, K and deflection and force are required to get this, or the stiffness is required to get this. I don't know the stiffness yet because I did not design the structure. So in order to get the period, I need the stiffness. And in order to get the stiffness, I need the period. So this is like the old joke that we heard it a lot. Which one came first, the chicken or the egg? Is the stiffness or the period? So in order to help us, the scientists and the seismologists, and they came out, Mr. Mansour will make your life easy. We'll give you approximation formulas. It's called T sub A, it's not actual T, which is the famous one is C sub T, H sub N to power X. Do you remember this? Or T sub A is equal 0.1 N. Or the famous formula, other one, T sub A is equal to the C sub G divided by the square root of C sub W times H sub N. These are 3 equations. They developed them for us in order to get the preliminary or the approximate period first. And after that, I will go and design my structure. And after designing the structure, I know the stiffness, and I can get the actual T based on the structure dynamics, based on the stiffness and mass, or mass and the stiffness. Do you see the approach of the code? So the code, this is called approximate approach, approximate period. Approximate period. And there is a relationship between this and this, by the way. There is one equation, they give it to us to compare this to this. Be careful. And I'm not going to explain every item. I need to focus on the problem. And after that, you are very welcome to tell me, can you go over this if you have a specific topic? I will be glad to devote. Okay, I still planning to have probably next time. I need to cover chapter 15 and chapter 16 again of my book. Chapter 15 is talking about the ATC, the Applied Technology Council, ATC 20 and 20-1, chapter 15. As I mentioned last time, structural dynamics, structural damage and retrofit based on the ATC 20 and 20-1. These 2 publications, I told you that try to get hold of them. This is ATC 20-1, and this is ATC 20. This is the second edition, by the way. But ATC-20, okay, is just still the first edition. I summarized, or I took many cases like this bunching shear. You will find it, what's a bunching shear is. So but I highly recommend you to buy these two documents or two references, because I cannot claim that I extract, because I cannot copy the book. Okay, I just took cases based on the work permit, based on the copyright, whatever the copyright they gave us. I took the cases that I need to discuss in the. So for some reason, when I was teaching the class last spring, chapter 15 and chapter 16, which is based on chapter 17 of the IBC, it's called structural tests and the inspection. I summarized chapter 17, but I always encourage everyone to get the entire chapter 17. This is the only chapter from the IBC or CBC. I'm asking everyone to get the full chapter. Okay, try to, if you don't have the code with you, try to secure a copy, because it's very, very important. Also, I summarize it as much as I can, and it has some tables. I extracted the table, whatever tables I extracted from there, but I cannot claim that I extracted everything. So I encourage everybody to get these two documents, the ATC 20 and ATC 20-1, plus chapter 17. And after that, you are very welcome to take any other codes with you. But those who use my books since the first edition, when I came with these books, when I was teaching this over here at CSU of Fresno and way back in Las Cruces in New Mexico, when I was teaching. So they feel that the book is self-contained, or it does have the information that they need. Yes, you are very welcome to carry all the references listed by the California board. You are very welcome to carry all of them, but there are 6, as you know. These are the 6 references, but you are very welcome to carry as many as you want. But what I heard from the engineers, this is what I'm trying to convey to you. So the period, so somebody may say, wait a second, can I use the T sub A here? T sub A is equal C sub T H sub n to power X. The answer is no, you cannot. Because I don't have this system listed, okay, under the equation. It has a table and it has systems, and it has what is the C sub T and what is X, the exponent X. So you cannot use it. So in this case, I will use this. Since I know the end conditions, and these two columns are in parallel. So right now I can get the stiffness, the total stiffness. Let me move to the following page. So I need to get K total, or the total stiffness. And since this is like spring, like this spring here, and there is another spring here. If you remember, we talked about this in chapter 5. If this spring stiffness is K1 and this is K2, so the K equivalent or K total, as if one spring, so K total or K equivalent is equal what? Is equal K1 plus K2. Why? Because this is a parallel system. If it is in series, the situation is different, but they are parallel. So the total stiffness is equal, since these two columns are identical, is equal 2 times K. And he told me that based on this 90 degrees here, and this is a rigid, that means that this is fixed top and fixed bottom. So it is 12 EI. So it is equal to times 12 EI over H cubed. This will give me K total. So here we go, 2 times 12 times, what is E? E is the modulus of elasticity for steel. He didn't give it to you. He did not mention, but he said that's just made of steel. So as I always joke, any civil engineer, even while he is dying, if you ask him what's the modulus of elasticity for steel, he should say, okay, he should answer. If he didn't need an answer, don't put him in the grave, including myself. Okay, just kidding. Okay, so there are two numbers, 29 or 30 million. It does not make any difference. If you'd like to remember, at 30 million PSI, I have no problem with that. This is PSI. Units are very important. I is given the moment of inertia, or the second order of the area, as some books they call it, but the moment of inertia is a common name, times 448 divided by h cubed. This is, by the way, inch to the fourth. Units are very important, but the height here is giving you 12 feet. So the 12 feet times 12 inches per foot, and this is cubed. Can you help me? I don't like to look to my solution because I need your participation. I need your participation. Let me get my calculator here. I think I have a calculator nearby. Here we go. And try to practice using the two calculators you take to the exam. I prefer three. Normally I prefer three, but if you like to stick with two, that's fine. Try to use these calculators on a daily basis, because so did I miss anything? Let me correct me if I'm wrong. 2 enter 12 times, 30 times, and 10 to the power 6 times, and 448 times, and 144 enter 3xy, inverse, recall this, and multiply. So I got a number. I hope this number is correct. 108,024.69. If you look to the units, this is PSI, pound per square inch. This inch to the fourth. This is right now inch cubed. So here it is inch cubed, and this is pound per square inch, so inch to the fifth. Here it is. So this will give you pound per inch, because this is the slope of the line. This is B and this is delta. K is the slope of the line, which is B over delta. B is in pounds and inch, so it is pound per inch. Anybody got something different from my number? As I told you, try to help me by looking to, and as I told you, I don't like to look to my solution, because and don't forget why two. For each column is this, but this is for two columns, because they are two columns and they are parallel. Make sense? After getting this, became piece of cake. So what's the period T? T is equal to pi square root of W. W is given. W divided by G times K. So here we go. 2 pi square root of W. What did he say about the weight? The weight is given to be 168 kibs. A kib is 1,000. So 168. This is kibs. I will say that times 1,000 pound per kib divided by G. G is 32.2 feet per second square. But I need it to be in inches, since I'm dealing with inches here, because the K is in inches. So in this case, I will multiply this by 12. 12 inches per foot. And finally, so this is G, and the K is, I just calculated to be 108,024.69 pound per inch. If you look to the units must balance. If they didn't balance out, that means I did a mistake. Okay, so feet will cancel with feet. Kib will cancel with kib. Pound will cancel with pound. Inch will cancel with inch. What is left? Second square. So this is going to be second square. Take the radical, it will be, this is why the period must be in seconds, S. Seconds. If they don't balance these units, that means that I did a huge mistake. And this is a very common mistake. Units, as you know, could be the source for an error. And generally speaking, if you find that your numbers or the number you are getting is so far from any given number among the four answers, that means it might be the units. So let's do this simple math very quick. So it is 32.2 times 12 times invert 168,000 times, I will take the square root and 2 times, and okay, where is my pi? Here it is. So I get a number very close to be this number here, 0.3986 seconds. Any different answer, please let me know if my math is not correct. And normally I do the calculation twice normally. So right now we have four answers. Hopefully that one of them is very close to this number. I have 0.2 seconds. I have 0.4 seconds, 0.85, and 1.4. Obviously, the 0.4 is my selected answer. As you remember that, or as you know, that you have 55 questions in 2.5 hours, which is 150 minutes, divided by 55 questions. This will give you the famous number, the 2.67, I believe. Yeah, 2.7 minutes per question. The question is, can you do this in this 2.7 minutes? Yes, the answer is yes. The answer is yes. I know we talked a lot, but the moment that you are ready for the exam, you're supposed to be. They might, and I have also some problems in my books related to this. They might give you a problem where the end conditions is different from fixed. So you don't use 12, you are going to use 3. Instead of 12 EI over H cubed, you might use something different. How? Let me show you. I believe I have some problems related to this situation, and hopefully I can find one of the problems very quick. When the moment I see the picture, I can, here it is. Okay. It is, if I didn't find it in 22 seconds, I will quit, and I can locate it during the break, and after that we can talk about it, where the end conditions are different from the fixed. It seems to me my 22 second already. So I will locate it during the break, or just to illustrate to you what different end conditions might exist and how this is going to affect the calculations. Okay, and I'll be glad to go over the problem. But so this is the first part. It's a problem number. The second problem is a problem 319, which is asking you to get what is the design base shear. But he didn't mention anything, but he gave me this. So if this is a problem by itself or standalone, as you can see here, you have to get the T first, which is a problem 318 or the previous problem. So with the 0.4, because I need to come here at 0.4, this is 0.1, and this is 0.5. So 0.1, 0.2, 0.3, 0.4, 0.5. I will come at 0.4. I will go at 0.4 until I hit the response, and I will go horizontally, take two straight edge with you, or two triangles, small triangles like this. You might need them. I get 0.8 G. And I need you to pay attention to this. 0.8 G. Some of them they have with G and some of them without G. The acceleration axis here, some of them they come with G and some of them without G. We said that the force is equal mass times acceleration. But W is equal mg. Or we can say M is equal W divided by G. So I can say that this is W divided by G times A. Do I have the weight? Yes, he told me this weight is 168 kips. The weight, here it is, the weight. So it is 168 kips divided by G. What is the acceleration? I get 0.8 G. So it is 0.8 G. G will cancel with G. And if you do this simple multiplication, you will get 0.8 times 168. It'll give you 134.4. And again, the answer will be in kips. And this is the answer D. Are you following me? Any question about that? So this must be given to you. Otherwise, if the response spectrum is not given, that means that he is asking you to solve it using the ELF or using the simplified or the alternate method. Okay, so he is asking problem number, since we are still here, problem 3-20, related to the same problem. And he is asking what is the drift, delta, lateral drift, or lateral displacement. Yeah, we remember that if you have a force F or P, and this is delta, so the stiffness K, which is F over delta, I need to get delta, so delta is equal F over K. So do I have the lateral force? Yes, we just found it, which is a 134.4 kips from the previous problem. Here it is, 134.4. Again, on the exam, he might give you this. That means that in order to resolve this problem, you have to find T first. Do you remember when we get the period T, and I came here at 0.4, and I went up until I hit here and get, and after that you have to get F or V slash V. And after that, because this is, I told you, if the base shear is V, so this is a force at that level, so you can say F slash V. So that means that in order to solve this, you need to do additional 2 steps before that. You get the period after you calculate the stiffness for each column, or since they are symmetrical in this case or identical, so we multiply by 2. And after that, I get the force, the base shear or the F, using the mass time acceleration. And after that, I will come and apply this. So in this case, but he might give you the problem and he will give you one of these parameters, assuming that the period T is 0.4 seconds, for example. So he saved 1 step. So the F is 134.4 divided by the stiffness. What is the total stiffness? Do you remember the total stiffness? We got it before, the 108, I believe. Here it is, the 108. Okay, 1024. So 108,024.69. But this is what? This is pound per inch. But this is kib, so I have to multiply this by 1,000. So if I do this calculation, so 134.4, and you multiply it by 1,000, and you divide by 108,024.69. Oops, sorry. Here it is. I get a number, hopefully that it is available. It is among the four answers, 1.2442 inches. And because so the bound will cancel with bound, because this is kibs. So you ended with inches, 1.24. So it seems to me the answer is B as in boy. Any question about that? So you need to read the problem carefully. You need to focus on the keywords. And after that, the strategy. You have to go to the exam with the strategy, because 2.7 minutes per question is not too much time. And I'm sure that if they allow you for extra half an hour, if they allow everybody to go extra half an hour, the passing rate will be extremely high. But unfortunately, the passing rate in the neighborhood of 1/3, about 33%, 40%, 42, 45 at the most. So between 30 and 40, it goes up a little bit, up and down. So about 40%, you can say about on the average, about 40% because of the time. If they allow everybody to go half an hour more than 2.5 hours, I think this percentage will go up sharply. Because I know you know the material, but probably the biggest enemy for you is the time. But so when you go to the exam, you must practice, and I believe those who you use these problems before and solve them, they told me, Dr. Mansour, it was more than enough. I'm not trying to say anything other than just what I hear, but the sky is the limit. Always I say that if you have any other sources or problems available in the market full of other books and all these things, or books and problems, try to solve it. No problem. I am not against any book, or I'm not against any other reference. But try to do your best. I've been doing this for almost 30 years. So before, almost, we had only two vendors at that time, Dr. Chalabati and Dr. What's his name? Chalabati and PPI, Mr. Lindbergh, the one I wrote chapters for him in his PPI serum book. So a lot of vendors available now, and they have a lot of books, maybe better than mine, maybe the same, maybe. So it doesn't matter. The ultimate goal is to prepare yourself. So you must understand the concept very well. Concept, number one. Number two, you must practice. And I say practice a million times, please. And after that, after you understand the concept, what we are looking for, and the practice by solving many problems, and don't look to the solution. Challenge yourself. Like right now, I could open the solution and read it for you, and that's it. No, we need to challenge ourselves. We need to look to what is this, what is why, and if I did a mistake here, where is my mistake? Challenge yourself. Even if you have a problem, okay, but in my textbook, for example, I have the 6 to 6, all the solutions are given at the end. Okay, the solutions given at the end. And if you find a typo or a mistake or an error, every time I come up with a new edition, sometimes they have typos or mistakes or errors, especially nowadays. I did most of the work by myself because my helpers probably will a little bit. So challenge yourself. But the textbook, I provide some problems. I call them the practice problems, for example, like this, or sample problems, it does have the solution immediately. I will cover the solution. I will get a card like this and cover the solution and read the problem and solve it. And after that, check to see if you agree or disagree. But at the end of each chapter, in addition to the sample problems, I add what is known as additional practice problem. Here it is. It's called supplemental practice problems. The solutions are given at the end. After you finish, you will find the solution immediately after that. Okay, but don't look to the solution because, or the solutions in general, because we need you to, okay? So this is, after we'll take a very short break, and after that I'll continue, but let me, one of you is raising the hand, and I'll be glad to answer question if, let me go to the hand first, and after that I will, let me see view. Okay, Omar, let me unmute you, my friend. Hopefully I can unmute you. For some reason, Omar, let me try one more time. Here we go. Oh, no. Oh, interesting. The rest I can unmute them except you, Omar, for some reason, but let me try one more time. Sometimes the for some reason I'm not able to, Omar. Let me one the third time. Why I am not able to unmute you? Let's wait probably after the break. Okay. If you can write the question, Omar, I will be glad to answer it after the break. And for sure I will try to unmute you. For some reason, it doesn't work with me. So I really appreciate if you can write the question in the question area. And after that, we'll talk about this after the break. Let's take about 10 minutes break right now. It's about 2:25 California time, so 2:35, please. Thank you. Okay, welcome back, everybody. So, okay, Omar, I'm still not able to unmute you. Hello?
Hello?
Now, okay, from your end. Can you hear me right now?
Oh, yes. I accidentally raised the hand. I
Okay, no
wasn't.
problem. But finally, we heard your voice. That's good. No problem. But fun. Yeah, some reason
Sorry about
that.
that.
Okay, no problem. No problem. Okay, thank you. Let me
Yeah.
mute. Sure. Let me mute. Yeah, now you are muted again. So good. So the so if you have any question, you are welcome to either to raise your hand. I will see your hand, and I will try to unmute you. And if it doesn't work, the other option is to write the question, and the question I will read it loudly. At least everybody will get the question. And okay, so going back to the seismic design requirements for building structures. So this is what I need you to be aware of as far as the following problem from the 6 to 6. By the way, as I said that, let me just, I started a statement and I didn't finish it. When I said that, when I was recording the class during the first quarter, chapter 15 and chapter 16 of my book, which both of them are based on the ATC 20 and 20-1 and chapter 17 of the IBC. For some reason, the recording corrupted or is not really, we cannot convert it. And obviously, if we are not able to convert it to the proper format that they are using with this company, so we were not able to load it. So the last lecture, for those who are watching the on demand, you will not find chapter 15 and chapter 16 of my book. I'm planning to cover them. I can cover them next time, chapter 15 and chapter 16. So let us set a date. At least you can put it in your calendar. It will be recorded and it will be okay. Hopefully this time it will work, and I will ask my assistant, the people who are helping me, even remotely, but they are still able to. So let us shoot for. So it is today is 5/17. So on Sunday, June 7, I will cover the two chapters, chapter 15 and chapter 16 of my textbook. Okay. So for those who are interested to attend the class, that's fine. If you cannot make it, it will be recorded. It will be available for the on demand. So this will be 6. We said that 6/7 or 6/6. 6/7. Okay. So just to make sure, 6/7. 6/7/20. Okay, and let me write it immediately in my notebook here. 6/7, June 7, which is Sunday. This is chapter 15 and chapter 16 of the seismic book. Okay, great. So the period T, here we were able to calculate it because we do have enough information about the weight of the structure, the stiffness of the structure, and so on. But if you are given a problem like this, and let me go to my textbook here, chapter 6. At the end of chapter 6, I have about 38 problems. So this book has about more than 200, and so try to do your best. So if you look to the one of the problems here it is at the end of chapter 6, you will find, and let us cover the solution so we can, or I can go over the solution with you this time. And so problem 6.4. He said that 3-story special steel concentrically braced frame, CBF, concentrically braced frame, with a penthouse, and the SDS and SD1 are given. And as you can see here, these values were given with the G. Also, we don't substitute for G, by the way, here. We do not substitute for G because also of the mass. The mass is equal W divided by G. So the G will cancel, and be careful about that. This is something very important, and I hope that you will not do this mistake. So the weight W were given, the height, and even he gave me the lateral displacements, delta 1, delta 2, and delta 3. And in the illustration, he gave you F1, F2, F3. So this, by the way, this is V. This is the base shear, which is the step number 1. When we calculate this one first, the base shear. And after that, we do the distribution. This is the force at each level. This came from equation. Let me write it down. F sub x is equal to C sub Vx times V. So the distribution is done according to this equation, where C sub Vx, if you remember, is called vertical distribution factor. Vertical distribution factor, which it has an equation I can write it right now, which is C sub Vx is equal to sum of the Wi Hi divided by sum Wi Hi to power n. Let me just double check the equation because I don't like to Wxhx. So here is a mistake I did. Okay, so it is Wx hx to power k divided by the sum of the Wi Hi to power k from I is equal 1 to n. Sorry for that. It's just so it's called vertical distribution factor. Here we go. And the exponent k, by the way, this is k is not the stiffness. The exponent k here is a factor to account for higher modes, and this it could be either 1 or 2 or linear interpolation, and I can talk about this later on. So but he did the distribution for you. So he gave you the forces, and he gave you deltas, lateral displacement, delta 1, delta 2, delta 3. And here is asking what is the period T. This problem is a little bit tricky because, as I told you, that the T, period T, the period T, similar to the equation we just used, which is the 2 pi, the square root of W divided by G times K, or 2 pi square root of M over K, or the general equation, which is 2 pi, the square root of the where is my sheet here, which is the sum of the Wi delta I square, the sum of Wi delta I square divided by G times the sum of the Fi delta I. This is the equation that's given in the code as a general equation, and after that we took this as a special case for a single degree of freedom. But this is a general. So the problem that is given here in front of us, I know the forces and I know deltas, so it's just a matter of plugging the numbers or putting the numbers. So this is the equation, which is the general equation, 2 pi square root of Wi delta I squared divided by G Fi delta I. And I ask here a couple questions. Can we use the approximate method for calculating T, which is a T sub A? The answer is yes, because I know the given height, h sub n. I can get C sub T and I can get the exponent x. So I can use the equation T sub A is equal C sub T h sub n to power x. Yes, I can. Yes. And I said here it is yes. Can I use Rayleigh formula, which is this one here? This Professor Rayleigh, by the way, he is a German scientist, to the best of my knowledge. And he did a lot of structured dynamic analysis, and he has some equations after his name. So the answer is yes, because I do have enough information. I have the weight, I have the displacement, I have the force at each level. So in this case, I can plug it in. And this is what I did. I took the first one, the first term, the numerator, sum of the Wi delta I square. And here we go. The second term, which is the denominator here. And remember this number here, this what is it? This is G. But this is 386.4 inch per second square. This is a 32.2 feet per second square times 12 inches per foot. If you multiply 32.2 times 12, you're supposed to get this number in front of you. Make sense? So, and it's given, if you go to my glossary and definitions, you will find, I will show it to you. But basically, the 32.2 times 12, so 32.2 enter 12 times, it gives you 386.4 exactly. This is inch per second square. So units again, the source for. So of the Fi delta I multiply each force times the displacement. And we ended with this. After that, we plug it into this equation. And units must balance out. This is kib inch square. This is inch square per second square. So kib will cancel with kib. Square inch will cancel. What is left is second square. If you take the square root, it will be second, and this is what we get. Up to this point, up to this, if I stop here, you will find the 0.74 is the answer D, and you may check answer D and go home happy. Say, oh yeah, I got all of them correct. And in fact, this is the wrong answer. If you go and check the answer D, based on your calculations is correct, or our calculation is correct. But I violated one of the code requirement. So if you pick the number that to matching this and go home happy, unfortunately, this is the wrong answer. Because the code, they said that when we do the analysis, there is a lot of approximation and a lot of parameters that we assuming that to be linear and. So they came up with this equation. This equation, it does not have a number. I give it number 6.1 because it is located in chapter 6. And this is the first equation in chapter 6. It does not have a number, or the equation that they carry number from the code. I maintain the number so you can go back and, for example, here it is. What is this? This is 15.4-6. This is not mine. This is not chapter. This is the ASCE 7-16, chapter 15. If you have the code and you open it, you'll find exactly this number over there. But if it is located somewhere, so in my chapter 1 or 2 or 3 or 4 or all the way to chapter 15, if there is any equation, so in this case, I give it a number. But they describe this, or they explain this. They are saying that the calculated T based on this equation, it should not exceed C sub U times T sub A. This is the approximate period. The one that is based on C sub T H sub N to power X. And C sub U is a coefficient. They give us a table in the ASE 7. And this table is, I can show it to you in just a minute. So I have to check this. And this is what I did. I said, okay, is 0.74 the one I just calculated using the equation? The calculations is correct, or the calculations are correct. Is it really less than or equal C sub U times T sub A? C sub U, I found it to be 1.44. And let me know if you have any problem to find where is the C sub U. I can show it to you immediately. And the T sub A, we can calculate it here. I know it's calculated in a previous problem, but let's calculate it. The T sub A is equal C sub T H sub N to power X. So there is a table for C sub T and X, which is this table here. This famous table, here it is. This is the equation. This table is taken from the ASE 7. C sub T, one column for C sub T and one column for X. C sub T has two numbers, one based on the foot or the US custom unit, and this is the SI units. So the number in parentheses, there is a footnote here. The numbers in parentheses here, they are in reference to the, or referring to the metric system. So I need to come and pick the appropriate value of C sub T, appropriate value of X, and plug it into the equation, and here's the equation. This is equation 12.8-7. T sub A is equal C sub T H sub N to power X. Sorry, the X is covered by, but the T sub A is equal C sub T H sub N to power X. This table is a little bit, it has a lot of systems, structural type, moment resisting frame systems, in which the frames resist 100% of so and so, and we have steel moment resisting frames, concrete moment resisting frames. and the steel eccentric breast frames in accordance with this table, so and so, line B1 and D1, and steel buckling restrained frames, and after that, all other structural systems. So you have to match the system that's given in the problem statement to match any of these rows, and after that come here. I did something to help you. I developed two tables for you, one for metric and one for English. So I give it a number. Again, if the table is my table, I give it my own number based on the chapter. But if it is a code table, I keep that. So this is a table using the equation. This equation is supposed to be ASC-16. Still the same equation, but it will be a good idea too. So I put the C sub T and X, and here are the equation, and I try to make it easy for you. So it is concrete moment resisting frame, CMRF, shear walls and other structure system not listed in the table here. This table, concentrically braced frame, dual system, steel moment, and so on. So if you go back to the problem we're talking about, we'll see what system is that, and it should match exactly. Here it is. If you go back to the problem, 6-4 of my book, by the way, this is page 248. It says concentrically braced frame, steel, special steel concentrically braced frame. So if I go to the table and to see match concentrically braced frames, and here I gave you the height, h sub n. This structure is 12, 36 feet. So I can come down. I don't have 36, I have 35. So 35 will give me about 0.288. Because if I plug it into the equation for C sub T and H sub N and X, so C sub T is equal 0.02, okay? And X is 0.75, so H sub N is 36, and this is 0.75. So if you do this calculation, you will get very close to 0.288, which is about 0.29. So 36 enter, 0.75, and you multiply this 0.02, so it's about 0.29 seconds. Or you can pick it, so you can use the equation, or you can pick it directly from the table if you have the height. Here the height is 12 and 12 and 12. I don't have 36, so I use 35, close enough. And as you can see here, the height of the bent house, this is called a bent house. What's a bent house? A bent house is a small room on top of the building. Bent house is a small room to house the electric equipment, elevator equipment. The height is not considered as part of the height of the structure. It's not part of the H sub n. From here to here, this is the H sub n. So after getting the T sub A, the approximate, I have to plug it into this equation, and this coefficient is obtained from the table, C sub U. Let me show it to you one. Here it is. I open the page and I'm like, here is the C sub U. C sub U table. C sub U. Based on the SD1. SD1 is given, so, and you can use linear interpolation, and this is what I did. So I plugged it here, and I ended with this. So the calculated period T, the 0.74, the one I calculated, it should not exceed the product of this, which it came to 0.42. So the 0.4 right now, so right now I have three periods. I have 0.74, and I have 0.29, the one I calculated. And I have the product of C sub U T sub A, which is 0.42. And you will find that all of them are listed here. 0.29 is listed as an answer A. 0.42 is answer B. 0.74 as an answer D. And he gave you another answer here to distract you. So all the periods are there. But one of them is correct and the other are not. And the correct one is B. So the code, it has some, and we do this, by the way, I wrote a note here just to bear attention that the above limit, this limit here, bears this equation, is applicable only for strength calculations, for the base shear calculations. For drift calculations, we don't have, without it, I can use a 0.74 directly. So the calculation for the period is very, very important, and you should know exactly what are the parameters that okay. Let us pick another problem. If you have any specific topic, please stop me and let me know, because I will be glad to discuss any topic that is still not clear to you, because we need to make sure that you really understand the whole subject, because I need you to pass the moment they open the barometric again. I need everybody to pass and forget it. Okay, no more headache and no more exams, and get your PE, unless if you like to go for your SE, this is different story, but again, try to do your best. Okay. Okay, the following problem, and also I'm picking problem related to chapter 6, which is building structures. And since we are on the same page, problem number 3, a 12-story building frame system structure with a story height of 12 feet. The fundamental period of the structure is most nearly building frame system, 12 stories, and is asking what is the period of this. And probably you can say that this problem is a little bit vague and is not completely written in a way to cover all the requirements of the code, which I agree with you, because we said T sub A is equal to C sub T H sub n to power x, or T sub A is equal 0.1 n, when n the number of stories, or the famous C sub D square root of C sub W H sub N. And this in the past, by the way, this last equation here, last equation is limited only to masonry and shear walls. Masonry and shear walls. In the previous code, it used to be written as 0.0019, but this time they put it C sub D because they are giving two numbers. So they call it C sub D, C sub G, sorry. C sub D, the other one, C sub G, okay? And the C sub G, it does have two numbers. Okay, one for metric and one for English. Or to be more specifically, C sub Q. Now, see my eyes, I'm getting, I need to make sure that we are using too many symbols and too many. So it is C sub Q, I'm sorry. First, I put C sub D, which is, C sub D is called deflection amplification factor. Okay, forgive me, too many. And C sub G, no, C sub Q. So C sub Q, it does have, it's 0.0019. This is an old one, feet. And for the metric, they are putting 0.00058 for metric. So the point is, this is the general. This one here, 0.1 N, where the N is the number of stories. But there are three requirements here for this. Number one, it must be steel or concrete moment resisting frame. So if you look to the equation 0.1 N, so instead of using the other equation, this way the code starts with the word alternatively, it is permitted to determine the approximate period, the approximate fundamental T sub A, using this equation, but not exceeding 12 stories. So the number of stories so N, which is the number of stories here, this, it should not exceed 12. This one required. Number two, the seismic resisting force system, or seismic force resisting system, must be consist entirely concrete or steel moment resisting frames. So this is concrete and steel or steel moment resisting frames. This is the second. And the third is with the average story height at least, so the height, we call it H sub S, by the way. H sub S is a story height. So the story height, it should be at least, so greater than or equal 10 feet. So we can use a 0.1 N as long as we meet all these three requirements, by the way. Not or, not this or this now. All the three requirements must be met in order to use this equation. So here, the problem I'm referring to in my book, what do you think? Is vague problem, or you can make a judgment and say, oh yeah, this is what he meant. Okay, so right now, 12 stories, so I did not, okay, exceed the, so the N is less than 12. I have no problem with that. Less than or equal 12, so I said 12. Okay, with a story height of 12 feet. Oh, H sub S is equal to 12 feet. So H sub S must be greater than or equal 10 feet. So already I have 12 feet. You see 12 stories and 12 feet water. Okay. And they said that is building frame system. And probably the word moment, it should be added to it. Because frame systems could be concentric or eccentric, but here it is entirely concrete or steel moment resisting frame. So probably the word moment is missing here. So the build is okay, the 12 story moment frame system structure. So by adding the word moment, I met all the requirements. And probably this is what I meant, but probably the word moment will clarify it, because frame systems only, building frame systems, this is category B, by the way. Category B in the table 12.2-1. You know the table, the big table, 12.2-1, which is the biggest table in the code. So category A is bearing wall systems. Here it is, category A, bearing wall. This is the biggest table, table 12.2-1, at the beginning of chapter 12 of the ASE 7. So bearing wall systems. The second group is building frame systems. And C, this is what is meant by this point 1N, moment resisting frame systems. So it must be under this category here in order to use point 1N. So probably I would add the word moment, building moment frame system. This is, he didn't tell me steel or concrete is not a big deal. It doesn't make any difference, but as long as the moment frame systems. So in this case, I met the 3 requirements as far as the number of stories and the height and the structural system. So in this case, I can say it is 0.1N. N is 12 stories, so 0.1N is giving me 1.2 seconds. Make sense? So I hope that the problems on the exam will be well, and for sure they write it and review it again and review it again and make sure that they are not confusing, they are not missing any word or any parameter or anything to make the problem complete. At least you can answer it. And I believe if I look to my solution, this 323. Okay. And I will stop. I said, oh my God, this is a moment frame system. But somebody may say, oh, the code said this and it said alternatively. Before I go to my solution, let me make sure that I complete the problem. Alternatively, because right now this doubt right now. Alternatively, I can use this, but the main one is here. Can I use T sub A is equal C sub T H sub N to power X? Yes. And this will make my answer here maybe not good answer. Or you see the question is really, okay, as I told you, tricky in a sense that, or probably the word moment, I dropped it intentionally. If the word moment is not here, I cannot use point 1N. No doubt about that. So in this case, I will go with the C sub T is equal point C sub T H sub N to power. So C sub T, if you go to the book, you will find that the C sub T for building frame systems is 0.02 and H sub N 12 stories and 12 height is 144 and X is equal 0.75 if you do this calculation, you will say that, oh, it is 144, enter, 0.75, and you multiply 0.02, I got 0.83, and this is the correct answer. So the answer right now is the D is the correct answer. So the word moment is not there, okay, as is written as my intention. But if he added the word moment, in this case, I have two periods, by the way. If the word building moment frame system, I can use 0.1n, but I have to check the other one because I can use it too. And in this case, which one I should select? If I have two periods, I need you to be aware of that. I'm glad that I hit this problem, at least you can. So if you have two periods, one is based on T sub A is equal C sub T H sub N to power X, like in our case, which is 0.02. The H sub N, they are 12 stories, 12 height, and 0.75, and we added 0.83 seconds. This is T sub A. But assuming that the word moment exists, he said that moment, okay, the special moment resisting frame, okay, as the requirements of the code, if he spell it out to be exactly as given in the concrete or steel moment resisting frames. So it is, if it is moment resisting frame, either concrete or steel, and it must be entirely moment resisting frame. So in this case, I use the T sub A is equal 0.1n. So if the word moment is added to the, so in this case, I would say 0.1. The number of stores is 12, and this is what I was discussing, 1.2 seconds. So I have two periods, and both of them are among the four answers. Which one should govern, or which one should be selected? V, by the way, the base shear, is inversely proportional to 1 over T. If you look to the base equation, the base shear equation, you will find it is inversible. So mean that the larger the T, the smaller the V. So if I'm designing this structure for a customer, my objective is to design it safe. Now, at the same time, it is very economical. Very economical means a smaller value of V. That means that the larger T will govern in this case, and this will be my selection. If, I'm saying if, the word moment is added to the problem to make sure that the three requirements have been met, that is a moment resisting a frame. If he would like to add the word steel or concrete, I have no problem with that. If he drop the word steel or moment, steel or concrete, still a moment resisting frame. And in this case, I will use the larger T, okay, of these calculated values. I do have a problem similar to this, if I remember correctly. in my book, because this could be a little bit that where the structure is eligible for both. Yeah, here it is. I have a problem. You have problem 6-7 of my textbook on page 251. For those who has the book, page 251. He gave you steel special moment resisting frame, and he gave you it is 7 stories. 1, 2, 3, 4, 5, 6, 7. We don't count the 2 levels below the base, the basement. So right now, if we use 0.1n, here it is 0.1n. So it is number of stories less than 12, story height with more than 10 feet. It is moment resisting frame. So in this case, so I use 0.1n, and the n number of stories 7 is 0.7, and 0.7 is here. However, I check the C sub t h sub n to power x, and it turned out to be 0.97. After I get the appropriate value of C sub t and the appropriate value of x from the table, and I can double check this, please. Here I have 2 periods. I have the 0.97 and I have 0.70. This is based on this equation, and the other one based on this equation. And both answers are here, C and D. But what I did select, I select D, which is a larger period. Based on that, the V is inversely proportional to 1 over T. So it's still safe. If I use a 0.97, I'm still following the code, but this will give me a smaller V. A smaller V, it will save some material for the owner of this building, because I'm designing for, you might say that, no, I need a smaller T to be conservative. I agree with you. If this is your luck to do this outside the exam, that's fine. It's your decision. That to be very conservative beyond the code requirement, you can use a smaller T, and this will give you a larger V. You may say this conservative, that's fine, I have no problem with that, but this is not for the sake of the exam. For the sake of the exam, the 0.97 is a correct answer. And if you get the ICC books, you will find that this is exactly what they are explaining. Okay? So all these things are really, really good, and I'm glad that we talked about this problem. That is, it does have the word moment. Okay, so here I don't need to check this at all, because the word moment is not, they said building frame system, which is system B, is not system C's. So all the systems under the moment frame, okay. So this is not applicable in this case, because it's not a moment frame. But if he add the word moment, in this case I have 2 periods, and in this case I'm still picking the 0.83, which is a smaller one, and in this case all these things are very, very interesting stuff, and I hope that you are catching all these little tiny things here or there, because okay, great. Anything that we talked about in chapter 4, by the way. Chapter 4, we talked about what's known as a damping ratio. Damping ratio. What is damping? Damping is dissipation of energy over time, mainly due to friction. This is the definition. Damping is the dissipation of energy over time, mainly due to friction. We remember in physics, the pendulum, this mass here, M, and we push this mass by a force F, so the pendulum starts to swing back and forth. Is the pendulum going to swing forever? No, not forever. It will stop. So the pendulum swing back and forth, it will stop. Why it will stop? Because of dissipation of energy or because of damping. The air resistance, the friction, whatever. We apply this to a building structure like this. The building, it starts to oscillate due to this seismic force, the V, or seismic activity. The building starts to swing back and forth. Is the building going to swing like this forever? No, it will stop. It will swing back and forth and it will stop. Why? Because of damping, which is a dissipation of energy. There is an energy came from the earthquake event, like the energy came from pushing this with a force, but the energy will dissipate over time, mainly because of the friction. So this is damping. However, each structure has its own critical damping. There is something is called damping and the critical damping. Critical damping is one unique damping that will bring the system to stop in a minimum time. So the system will stop from oscillating at minimum time. So there is one damping, one specific damping where the system will come to a complete stop in a minimum amount of time. Minimum time, this is a key word here, minimum time. This is called the critical damping. The ratio between the damping and the critical damping, they call it damping ratio. And this is, let me bring my book here, chapter 4. If I remember correctly, sometimes or maybe chapter 5. Yeah, chapter 5. You see, I told you that. Here it is. Equation 5-8. So the ratio between the damping coefficient and the critical damping is known as a damping ratio. Damping ratio. So damping ratio is, they use the Greek letter zeta, is equal the the damping of the system over the critical damp, over its critical damping. This equation 5-8 on page 115. And this is the graphs that I explain. A system without damping, there's no damping at all. Here it is, no damping. It will keep oscillating forever. You see the commercial diamond forever, and this is okay, oscillation forever. So the system will keep oscillating with the same amplitude and the same period forever, but there's no such thing exist, because we do have underdamped system, overdamped, and the critical damping. So the system will start to die or the oscillation will stop because of the damping. So there is a table here. It's available in most of seismic design textbooks. Damping ratio for buildings, for building structures. Steel frames, they have damping ratio between this range. Concrete, masonry, concrete shear walls, and finally wood frame. And as you can see, the wood frame, it has the highest. And as you can see, the arrow is increasing this way. So a question like this, yes, it will take less than 2.7 minutes, because if you know the source, and here it is, that plywood shear walls have the highest damping ratio among other structure systems, such as concrete shear walls, concrete multi-resisting frames, so and so. A higher damping ratio would have which one? Have the following effect. The damping ratio. We said that, yes, wood, it does have the highest damping ratio. But this damping ratio is good or bad? It will decrease the seismic base shear. It will increase the period of the structure. Or it will increase the natural frequency of the structure, or the answers A and B. Okay, what do you think? And let me remind you of something. This is the structural period, and this is the acceleration. Acceleration. You will find that the response spectrum goes like this. It will increase to the peak and come down. As the period increase, the acceleration will decrease. So at higher period, you will find that the acceleration will be less and the seismic force will be less. Because the seismic force, it depends on the acceleration. Because force is equal mass times acceleration. So decrease in the base shear. No doubt, yes. Is going to increase the structure bit slightly. It will increase a little bit, and this is why the base shear is coming down, because the acceleration. So the answer A and B are correct, and this is why we selected D. Another problem 3-322. 322. The following table shows two single degree of freedom SDOF systems with different properties. The mass system 1 has 4m, and this other system has, and the period is T, and here is 2T. Which of the following statements is correct? So you give me the mass, and the period. Here you can say the base shear and the base shear stiffness stiffness. So it's dealing with 2, is basing with the base shear V, and these 3 answers is the stiffness K. Comparing the 2 stiffnesses, and here comparing the base shear here. If the base shear for system number 1, you have 2 systems. This is a system number 1, and this is a system number 2. Okay, the mass of this is 4m, and this is just only m. And the period, this is just T, this is twice T, 2T. So I have the period and the mass. And he said that the base shear for system number 1 is equal the base shear for, no, I cannot do this calculation, no. In fact, V is inversely proportional 1 over T, by the way, if you remember. The larger the T, the smaller the V. So, and this is a larger period T, so I'm expecting the V will go down, like the response spectrum, as I told you, that as the T increase, the acceleration will go down. So this is out. Right now, he's talking about the stiffness. So right now, we just use an equation. We use an equation to calculate the period T. So T is equal to pi square root of m over k. So if I calculate for system number 1, I will say T square is equal 4 pi square times m over k. System 1, if you remember, the problem statement say that this system has 4m, and the period T, so I will say that T square is equal 4 pi square, m is 4m, and the stiffness K. Here I can solve for K. So K is equal to 16 pi square m divided by T square. This is for K number 1. This system number 1. System number 2, he gave me other parameters. He said that this is only 1 mass, but the period is 2T. So I will apply it here. So it is 2T excuse me, 2T is equal to pi square root of m over k. This is for system 2. System 2, it has only 1 mass, m. So I put only m here, I put 4m. So in this case, I can say that I square it. So this is 4T square is equal 4 pi square m over k. And from here, I can solve for k. So k2, 4 will cancel with 4. So it is pi square m divided by T square. So this is the stiffness for system number 2. If you divide these two, so pi square will cancel, m will cancel, T square will cancel. So K1 over K2 is equal 16 over 1. So K1 over K2 is equal 16 over 1. Or you can say that K1 is equal 16 K2. So the stiffness of system number 1 is equal 16 times of the system number 2, or the stiffness number 2, and the answer is D as in David. Are you following me? Do you agree or disagree? Agree or disagree? All these problems, I hope that it is building your knowledge and your understanding, because when you go to the exam, you will not find any of these problems on the exam. Okay? It doesn't matter if you collect all the problems available in the market, they will not really, they come up with always with the new problems, something is not available in any book available in the market to the best of my knowledge. But the question is, do I understand the concept? Do I apply the concept correctly? Yes. So in this case, it doesn't matter what problem he's going to bring over, or what set of problems or set of questions he will bring over, as long as I am applying the concept correctly. In this case, we are in good shape. So we cover this page 3-18, 3-19, and 320, 321, 322, 323. Plus, I believe we'll solve other problem. I can't remember if I solved. Yeah, from the book, from the textbook, which is, at least when I make a copy for those who don't have, if you don't have my book, at least you have the this problem here. The one it has the calculation for to check this. This is a very tricky, by the way. This is very tricky, and we need to double check this, please. Okay. Okay. So, any other questions related to the seismic? Anybody is taking the exam this month, by the way? I think the month. Anybody? Do you know? As I said, that I didn't check the Prometric website, the California board website recently. Anybody is taking the exam this month? This month, anybody is taking the exam this month, the month of May? Anybody is taking? You don't have to tell your name. Anybody is taking the exam in June? Anybody is taking the exam in June? Just raise your hand, okay? Because I would like to see what. So we have May 17 today. So we have June 7, where we are going to cover chapter 15 and 16, and this will take about 3 hours, or maybe the entire 4 hours. Yeah, I believe maybe it will take the entire 4 hours. It depends on the questions. So please try to attend chapter 15 and chapter 16. I'll explain it very well. And for some reason, if you don't have my book, and I will be glad to email these 2 chapters to you, with a promise that you will not put it on the internet. I will be glad to send it as a PDF, but don't load it on the system. Okay. And after that, so this will be, and we still have 2 periods in June. Okay. Obviously, after the second quarter, this is the second quarter. The third quarter will start, and most likely it will be similar to this, because already I taught the class in the spring, and the spring 2020 I have the on-demand. So the on-demand, it does have all the lecture. So which is this one here, 24/7 available to you. So okay. Any other questions or any? So nobody is taking the exam even in June until now. Nobody. Okay. So maybe some of you. Okay. I saw something here. I got an email from the board that we will need to retake exam after July. I was originally scheduled for June. Oh, since he already received an email, okay, our friend Okay, it's telling me that. Okay, that's after July. Reschedule the exam after July. So because yesterday I was teaching the surveying class. I have a surveying class, and this is based on the second edition of my textbooks. And they are saying that there is a huge demand for the barometric sites or the testing sites. So you have to reserve your spot as early as you can, because I believe because of the cancellation. So there is too many engineers are trying to take the exam. So try to reserve your spot as soon as you can. So so there is no exam in June. Okay, that's fine. This will give us even more time so we can explain more. But I need you to work the problems. I need exactly like the way I did it right today. I need you to set. Okay, either you have two options. Let me get my camera here one more time. You need, okay, either to work it exactly like this. Okay. And don't look to the solution, or if you have already the USB, so you have the problems, and this will simulate the actual exam. So in this case, I have no problem with that. That if you are solve it like this. In fact, maybe I would say that do it both ways. I will solve it like this, hand calculation like this, and after that you can start to practice as many exams as you can, because our system. Okay, so I have to stop here because I'm not really feeling well. I'm still fasting. Today is the last weekend of Ramadan. Okay, so Ramadan will be over this coming Fridays. Those of you who are familiar with Ramadan, we are fasting since 4:30 in the morning. No food, no water, nothing except just fresh air only. Okay, air free from any corona. So I'm not feeling well. So let me stop here, and I owe you an hour. So when we come back on June, okay, I will be eating for sure, and in this case, I will be glad to help you. But you are very welcome. If you ask me a question right now, I will answer it. I'm not. I have only 2 calories left, but that's fine. I can burn 1 calorie to answer any question, and keep the last calorie to for some reason today is. But I'm glad that I was able to make it. I was thinking that I will not be able. I would think that, but I was so glad. But please go over these problems. These problems, based on what I heard from the engineers. If you didn't practice, I'm sorry to say that the chance for passing will be small. So try to practice as much as you can. Practice as practice and the practice and the practice, as I mentioned, million times, and look for keywords. For example, here when I read this problem, I said, oh, okay, probably the word moment is missing, and they say, oh, probably he meant that. No, this is what he meant. Okay, so I cannot use 1.1n. So in this case, you see, this is the thing that I needed to do it in your own, and I wish you the best. Okay, so I will stop here, and thank you very much for coming today. This lecture will be loaded, available for you today. And when we meet next time, I want to cover chapter 15 and 16 of my textbook. And for those who are having the book, and study hard, and work hard, and come up with questions. The more questions that you ask me, the better at least for you, because I will clarify whatever question that you have. And if you find a typo or a mistake on my books, please let me know. I'll be glad to correct any typo or mistake. Nobody above mistakes. Okay. Thank you very much, and appreciate your coming today. And let us meet again in 2 weeks, and where I cover chapter 15 and 16. Good night, everybody. Bye-bye.